Hi everyone. This is a demo. In this demo I'll show you how to use Numpy, and in the way of doing this I'll show you how to access your projects, the assignments rather, for the course. So when you log into Sage Math Cloud now, since you're joined in this course, you should see something like this. I've added you to two shared projects. One is this shared project where you can edit and share files with everyone in the class, and the second is your assignment page. So this one that says Michael Forbes Physics 521, that's where my assignments will be. So I'm going to go into that one. That's my personal one. I don't share it with anyone else other than myself and the instructor, which is also me. So when I log in here right now, I've assigned two assignments that aren't due. The due date is the end of the course. One is tutorials and the other are demos. The tutorials will contain things that I think are very useful, should be useful for you, background into things like Numpy arrays, that's what we'll talk about today. And the demos will contain things that I'm trying, more complicated problems, etc. Now, warning, both of these I will update periodically. When I update them, that will overwrite any work that you do in these directories. So if you want to work with one of these files and use it for something else to modify it, then please take that file, select it on the left, and copy it up here to a new file, say in your home directory. So if I were to do this, then when I go back, I should see it in my home directory. Now this is my version. You can do whatever you like with this version, and I will never touch that. That will never get overwritten. So just caveat, tutorials and demos will be overwritten at times. All right, so let's go into the tutorials, into the Numpy arrays tutorial. Here I've tried to put all the interesting features about Numpy arrays that you may need during the course of this program. And I will just do a quick overview of some of these. Numpy is the package in Python that provides access to an underlying array structure. This array structure is the same structure that's used in C and Fortran. The default ordering is in C. Underneath there's a pointer, and you can access that pointer if you need to. So if you need to call code in C or Fortran that expects your data in an array, Numpy is the way to do it. You can populate the array in Python, and then you can pass the pointer, etc. But forgetting other languages for now, Numpy arrays are basically a way to keep track of a list or a whole bunch of numbers in an efficient manner that allows you to do very efficient coding. So the first thing to do is import Numpy, and we're using the convention here of calling Numpy NP. That's pretty standard. I need to wait for my kernel to start. Let me just restart it, make sure it's running. Okay, kernel was ready. All right, so now I can shift enter. All right, so I've imported Numpy. Now, there's many ways to create an array. You can create an array from anything that you can iterate over. So here I have a list of 3 elements, 1, 2, and 3, and I'm going to use np.array to turn that into an array. Once I've done that, I've printed various things. I've printed the array itself. It looks kind of like a list. I've printed its shape. Its shape is 3. It has 3 elements in it. Now notice that the shape is 3 comma. Numpy allows for multi-dimensional arrays, as we'll see shortly, and so the comma means that in principle there could be additional axes. But this particular array is one-dimensional, and it only has one length, which is 3. And the D type, that's the data type for the array. And in this case, it's an integer, a 64-bit integer, so that's where the data type is. Arrays work best if all the data in them are the same. You can actually use multiple different data types, but then they get converted to Python objects, and the efficiency goes out the window. You can create a range of numbers. This is like the Python range command, but it's a bit more flexible in that you can create fractional steps. So here we create an array from 0 to 9. Not including the endpoint of floating point numbers. You can create linearly spaced points. So here we have 11 linearly spaced points between 0 and 1. This includes the endpoints. And this is very useful if you want to make a set of abscissa, for example, x values to use for plotting a function. You can create some special arrays. For example, you can create an array of zeros, or you can create an array of ones. These ones is very useful if you want to create an array of some constant number, just multiply something by it, like a 3 or 4 or something. Okay, so we have these. Notice these shapes now. These are multi-dimensional arrays. The zeros array has 2 items down, and so 2 rows, and 3 across. So if you take a look at this here, the shape is 2, 3, 2 down, 3 across. The other one is 3, 2. It's 3 down, 2 across. The identity matrix is obtained with np.I, UIE, that's shorthand for identity matrix, and it is square, and this is a 3 by 3 identity matrix. You can also make matrices with diagonals. So here what I've done is I've created a list with 5 elements. This is a shorthand for creating a list. If you multiply a list by a number, it will make repeated copies. So this is 5 copies of the number minus 2. Another way of doing that is to use the np.ones array. So here we've created a 4-element list, or it's actually an array of ones. And so you see that here. This was the 5-element array of minus 2. It's a list. And this is the 4-element array created by ones. Now, I'm using the diag command to make a diagonal matrix with d0 on the diagonal. And I'm adding to that a diagonal command with d1 on the off-diagonal up one, and then another one on the off-diagonal lower one. And you see the resulting matrix here is what we talked about in class. Oh, sorry, that's not it. Here's the resulting matrix. It's a 5 by 5 matrix. The diagonal entries are minus 2, and the off-diagonals are 1. And this would be a suitable matrix for computing a second derivative. You can also use the diag command to extract the diagonals from a matrix, and if you use it twice, you'll get the original matrix back, but with only the diagonals. So this is just the 2's along the diagonal. So that's quite useful, especially if you're going to do derivatives and finite differences and stuff like that. Numpy also has random numbers generated. So here we generate a multi-dimensional array, 2 by 3 by 4, so it's like a cube, and it has random numbers. If you're going to use random numbers in your program, I highly recommend that you use seed first of all, because this will allow you to reproduce your results. Okay? So here we'll just create the array. Here we have this array. Notice it has multi-dimensions here. All right. Now, I have an advanced topic here about performance. I will skip that for now and come back and discuss that later. Now, if you want to manipulate arrays, then it's useful to have, here I've just created an array with a bunch of strings. And these strings are indexed by the same index in the actual array. So I'll show you how I use this. This is a little bit complicated, don't worry about it, but this is useful for visualization. If I take the 0, 1, 2th element of this array, it is the string 0, 1, 2. So you can see where things were. The 0, 0, 2 element was 0, 0, 2. So it's useful once you manipulate the array to find out where everything went. This is a quick way for doing it. Slightly advanced topic, we'll talk about that later. Now, we have that array up above. Let me just show you how you can index into an array. So here we create a simple array, which is the numbers from 0 to 4. 0, 1, 2, 3, 4. Now, this command here indexes from the start of the array to and including 2 elements. Okay, so it's up until including 0 and 1. Indexing in Python goes from 0. And the thing after the colon typically means how many elements you're going to get. So you see, if I do that, I extract the elements 0 and 1. If I do it the other way, n of 2 colon something, that goes from the second element to the end. Now notice this goes actually not from the second element, it goes from the element with index 2, which is actually the third element, and that will get the rest of the array. So these often work together to partition an array into 2 parts, the front part and the back part. You can also index relative to the end of the array, so minus 3 gets the last 3 elements, so you see that here. 2, 3, 4. And then you can index in a little bit more fancy ways after the second colon comes the spacing. So this is indexing from the beginning to the end, because I've left those blank, so nothing there before the first colon, from the beginning to the end in steps of 2. So that actually gets all the even numbers, 0, 2, and 4. And the second one starts at the first element, goes to the end in steps of 2, so that'll get all the odd elements. So there's some fancy array indexing that you can do with this. With Numpy, you can't do this with lists, but with Numpy, you can actually use lists and other types of indices inside here so that you can extract whichever elements you need. All right, you can also use indexing on the left-hand side. So here I am referring to the elements from 1 to the end in steps of 2. So those are all the odd elements. And I'm actually assigning those now to be the negative of values of what they were before. This will mutate the array. And so now you notice my original array n is 0, minus 1, 2, minus 3, 4. So on the left-hand side, I've referred to a subset of the original array by this indexing, and I can actually assign values to those. All right. Now in multiple dimensions, if you have a multi-dimensional array, then remember our matrix A, which was a 2 by 3 by 4 three-dimensional cube. If you just give it a single index, then it pulls out one entry from the cube. So this is a subarray. This is equivalent to going A colon 0 comma colon comma colon. That pulls out everything in the second and third index, but refers to the first index as 0. So it pulls out a subview, which is now square of the original array. Let's just see that those are the same. They are. And if you don't want to type out all the indices, you can use a shorthand, which is ... That refers to any indices that are required to fill out the array. Okay? And the second one is equivalent to putting on 1 in the first index. All right. Here's again a subarray. We take the entire set of the first index, the first element, so the one element, which is the second part of the second index, and from 2 to the end of the third index. So this is a small subset of the original array, and here's the ... notation again. This gets everything from the second index from 2 to the end, and all of the first indices. So all the zeros, all the ones in the first 2 spots. Okay, take a look at the entries that are in here and play with this a little bit so you get comfortable with it. It's a little confusing at first if you've not thought about multi-dimensional arrays. Hopefully with this matrix, not matrix, array A, with the strings you can see what's happening. Numpy arrays can be converted to various types, so you can convert them to floating point strings. This is an array of strings, but you can convert them to floating point numbers, to integers, etc. And if you need to, you can convert it to a set of nested lists. That can be useful at some point if you need to manipulate it. Finally, a very useful command that you'll need quite often is the ravel command. This takes an array and represents it, pulls everything out, ravels it into a single list, or a single array rather, of one dimension. So it takes all the elements and just flattens it out as they're stored in the array. And so this can be very useful if you need to, for example, to modify every single thing in the array. Once you have a raveled array, then you might want to do something with that. So here I will use a list comprehension. I'll add a string 9 to each element in the array. So 9 plus x for x in the raveled version of the array. Okay, so now I have a list of the strings like this, and then I can convert that back to an array and then reshape it into the original shape of A. Okay, so this would be one way of applying a function to all the elements in a matrix or in an array and then getting back into the original shape. All right, transposition reverses the order of the indices. So you can see here it went from 2, 3, 4 to 4, 3, 2. That's very useful. For matrices it makes sense. For multidimensional arrays it reverses all the indices. And then there's some other commands that will allow you to reshape arrays, such as roll, which takes axes that go around. And these are very useful for tensor manipulations. So here, for example, we'll look at a matrix A, which has 3 indices. We've called them A, B, and C. And if we roll this, it's equivalent to defining a new matrix with the indices in a different order. So you can check this through and see that that converts up here. Now, when you have notations like this and you want to use indices, especially with the Einstein summation convention, then Numpy provides a very useful command called einsum, which stands for Einstein summation, and it allows you to directly compute expressions like this one here. So this was, remember, the Levi-Civita tensor we used for rotations or cross products, and I'm summing over the I index here, and I want to prove this identity that it's proportional to the delta functions this way. So the first thing we have to do is create a Levi-Civita tensor. And so I've created an array that's 3 by 3 by 3 with zeros. And then I've set the 0, 1, 2, the 1, 2, 0, and the 2, 0, 1. These are all the cyclic permutations of the original permutations, 0, 1, 2. So these are all the even permutations. I've set those all equal to 1. And I've set all the odd permutations equal to -1. Okay, delta is the identity matrix, so it's np.I. And now I'm going to do the expression up above, which takes the index ijk on the first Levi-Civita tensor, and the indices ILM on the second Levi-Civita tensor, and it will sum over the repeated index I, and it will spit that out into a four-dimensional array that has indices in the order of j, k, l, m. That's exactly what our expression here wants to do. And so we can provide the indexing in a string, and then provide the two arrays as an argument, and it will compute that Einstein summation. The second way we want to do this is the expression on the right-hand side of the equal sign, which is the deltas. So we take delta JL and delta KM and turn that into a single entry, which has indices JKLM in that order. And in the second one, we do the same thing, but now we reverse the order to JM and KL. Put those all together, these two matrices should be the same. And we've put an assert statement here that checks that they are indeed the same. It's very useful to include assert statements in your code just to make sure things are working. You can leave them there, and you can actually run Python in a way that will ignore those so they won't slow down your code. All right, one more example here. If we sum over two indices, I and j, we should get a single delta function, which is the identity matrix. And so we've done that here, and you can check that when you do this summation, you indeed get the identity matrix with a factor of 2. Okay. There's some few additional things here, discussion about performance, etc. We'll talk about that in a later tutorial. Finally, let's talk a little bit about broadcasting. So here I am creating an array x with points from -1 to 1.5 to 1.5 linearly spaced at 5 points. Okay, so that is a one-dimensional array, the thing that I've highlighted. Now, I want to represent a function in two-dimensional space, so that if you want to represent something with 2 dimensions, then you have to have a square matrix. No, it doesn't have to be square, you have to have a two-dimensional matrix. So what I'm doing is I'm broadcasting this single vector, single array of x's, into a column vector. I'm putting all of the elements down the column, that's what the column means, that's where they go, and I'm inserting a blank axis in the horizontal direction. So this becomes a column vector. With y, I'm doing the same thing, except I'm now inserting it not down the rows, but across the columns. So I'm making a real row vector here, not just a vector, but a row vector. So let me just, before we do this, let me just show you what these look like. So if I just took the linearly spaced points, you'd see that's a single array with one dimension, and its shape is 5, 0. Or 5, nothing. There's only one dimension there. Now if I take this and I broadcast that, it becomes a column vector which has shape 5, 1. So at 5 down, 1 across, this is now a two-dimensional array which represents a column vector. And if I put the none first, it becomes a row vector, 1, 5. Looks like that. And you can add as many nuns as you need in order to get the shape that you need. So this is a 1, 5, 1. Now the interesting thing about Numpy, this what's called broadcasting, is when you do this, you can then use this as a replacement for a matrix that really is very large and has repeated columns or repeated rows in such a way that you can compute something. And so here what we're doing is we are computing a function f of x squared plus y squared, y cubed rather, and the x's are broadcast down and the y's are broadcast across, and when we add these together we will get a two-dimensional array that represents the function f of x, y in that 2 dimensions with the x changing in the downward direction and the y changing across. And then we can use that and we can plot things with that. So this is the notion of broadcasting in Numpy. Now, just one warning here. Many of the plotting functions in Python, which come from the matplotlib, which we'll discuss elsewhere, have correspondences from MATLAB functions. And MATLAB uses a different indexing convention where these matrices actually have to be the transpose of each self. And it's based on the idea of trying to load images. It makes a little bit more sense when you're trying to load images from a file on disk. So the standard function in MATLAB for creating such an x and a y is called the mesh grid function. But it is different from what we've done above by a transpose. So if you want to use the MATLAB convention, you have to take the transpose of the matrices we had above, and this really only makes sense for 2 dimensions, which is why I don't like to use it. What we've done above makes sense for arbitrary dimensions. You can trick the mesh grid command into mimicking the behavior we did above, but it's easier to do what we just did above, so I just leave that there. Let's just take a look here. So notice that the mesh grid command gives you a matrix that has repeated, in this case, repeated rows. Okay, and then the other one has repeated columns. And if you compare that to what we did before, we had a single column representing the entries for the y direction, or a single row representing the entries for the x direction. And that forms a stand-in that will get converted to this full array when needed. Okay, think a little bit about this code and think about this function, representing this function, and see if you can figure out how broadcasting works. Let me know in the discussion forums if you have any additional questions about that. Finally, once you have this function, we can do things like pass this to a contour plot function, which generates the contours for this function. And you'll notice here that if you're using the convention that I've used, not the MATLAB convention, you have to take the transpose because this plotting function indeed wants the indices in the order that MATLAB expects them. And so that's a little bit of a quirk that you have to just get used to when plotting. We'll discuss plotting later. Finally, if you have a matrix or an array or something that you want to save to disk, there's a nice function that does it called saves, and you can save it to a file. And then later on, you can load that file up, and you can access in that file the keys, and you can get the original arrays and check that they are the same. Now, you have to be very careful. Use this for Numpy arrays. Generally, you can actually use it for things like dictionaries and stuff, but it's really inconvenient for that because it stores this as a Numpy array, and when you load up C, which was a dictionary, it converts that dictionary into an object array, and then you can't actually extract it as an element unless you ravel it first. So anyway, this is a little bit confusing. There's a Stack Overflow question that discusses this here. So generally, if you can get away with it, only use saves to save array data, and then load that up into your program. And there's a few other things here for sorting and finding the minimum argument and stuff of arrays that I will discuss at some later point when we need those. Okay, so there's a quick overview to how Numpy works.